kind of a unique one, and I don't know that this, in this particular form, would show up on an AP test, but it is, in the interest of thinking about you guys moving forward into college, it is a common question you might see in a College Calculus 1 scenario. Number 5, there's just a trick to it. Do you guys remember what the trick is? You might have seen this in pre-calc. Rationalizing the numerator, not a common thing, but in this case, it's what we do. So we would multiply the top and the bottom by the conjugate of the top. Again, kind of an odd step, not one that we're really accustomed to, but that's what we do here. So square root of x plus 1 plus 2, and same thing in the denominator. The one thing I'd encourage you to carefully consider here is that when you do multiply it out, I think we should probably go ahead and multiply the top out completely, but don't FOIL the denominator, because if you FOIL the denominator, you probably won't see the cancellation that we need to have happen. So if we progress on to another step, the top, square root of x plus 1 times the square root of x plus 1 is, of course, just x plus 1. And when you create a conjugate, doesn't the multiplying out of the conjugates end up canceling out the middle terms? They add out. That's kind of the whole point. And so when I multiply my outers and my inners, I'll just get opposites and they'll add out. So I really only have to worry about the f and the l in FOIL, right? So negative 2 times 2 is minus 4. The denominator, I've still got x minus 3. And I've got that root x plus 1 plus 2 hanging out there. The point being, if you don't FOIL the denominator, can't you now see the cancellation? In the top, essentially, we've got x minus 3, and we see that other factor of x minus 3, so that means this cancels with that. And now we've gotten rid of that factor that was causing us the issue to begin with, and now we can go ahead and evaluate the limit. So if I take that 3 and I try to directly evaluate it, 3 plus 1 is 4, the square root of 4 is 2, and 2 plus 2 is 4. So we end up with 1/4. So that multiplying by the conjugate of the top and bottom there, is kind of that little tricky step you'd have to remember if you were doing a question like that. And maybe you recognize this is actually the definition of the derivative. I'm getting ahead of myself a little bit, but the definition of the derivative of a square root function, evaluated at 3. So something to think about. Okay, so kind of the main thing is, as we kind of finish up this little section in the chapter, I want to move ahead and do, I think it's 6, 7, and 8. Okay, so I want to see if you guys can handle those on your own. In large part, they're kind of like things we've done recently. Just give it a shot yourself. 6, 7, and 8. Is 8 a graphing calculator? Yeah. Okay, cool. So give it a shot. Give you a few minutes to try that. So with number 6, let's double check and make sure we're in good shape there. You try direct substitution, you end up with a 0 in the top, which is not a big deal, but you end up with a 0 in the bottom, which is a big deal. It's a problem. So we got to go back to our algebra skills on this one to try to get things simplified. Did you guys factor the bottom? Did you factor out an x? Okay. So your next step could look like this. Limit as x goes to 0 of x over x parentheses x minus 1. The x's then cancel out. And then we've got limit as x goes to 0 of 1. It's supposed to be a 0. 1 over x minus 1. So did you all end up with 1?
No. -1.
Negative 1. Awesome. Okay. Do you have any questions? And then number 7, really, I don't know that there's a lot of steps you would show on something like that. You're really looking for a pattern within the table. What pattern do you see? As x goes closer to 5, the y values are approaching 11. Yeah, in situations like this, we probably want to assume an integer value. So I think 11 would be reasonable, although it would be hard to defend that against 11.000001. So we're really thinking of this as an estimate, right? The best estimate we could. Reasonably, probably 11 makes sense. Okay, and then what did you think of number 8? Number 8 is kind of interesting because when you think about like the direct substitution idea, it definitely doesn't work. And I feel like there's like some really bad math waiting to trap you. So, I can see how someone might look at that and be like, oh gosh, plug in a 0, doesn't work. Now, nobody in here would ever do this. It would have to be some other kids that I've seen in the past, but maybe they would go, And then we start doing crazy, oh yeah, sine of 7. Or, I don't know. Or maybe 7 sine, who knows what somebody might do at that point. But obviously, I hope that that's really horrible, horrible bad math. In fact, I'm going to erase it really quick before somebody sees it. You simply can't do that, right? You can't cancel the input of a sine function with some other factor in the denominator. Just really, really bad math. It's like saying, well, I don't know what it's like saying, but it's really bad. So that's why I used the hint of a graphing calculator to help you. Did anybody go to the table on the graphing calculator? Anybody? What happened when x is 0? Error, but then all the numbers around that were there, right? There was plenty of outputs for all those inputs. And did you notice that from the left, it's like 6.99999, etc. And then from the right, it's kind of the same thing. So you can, from that table and really from the graph, draw a conclusion that the answer is 7. Yeah, so this ends up being 7. Kind of a unique situation here. This is one of the few times, I guess maybe in pre-calc, when you were looking for a vertical asymptote, didn't you look for zeros of the denominator? Remember that? Looking for a vertical asymptote. Well, think about it. Isn't a 0 of the denominator 0? Like if you plug in a 0 for x, the denominator is 0. But is there a vertical asymptote right there? Look at your graph. Does that look like a vertical asymptote to you?
No, it's just a hole.
It's just a hole. So that notion of the zeros of the denominator are always vertical asymptotes, we should probably take the word always out of that. It's not always true. It's often true, but it's not always true. This is a case of that. And so this question in and of itself, I don't know, using the graphing calculator, I don't know that this would be something that we would test on a lot, but you're going to learn a technique to deal with this where you can do it analytically instead of my calculator told me. We can actually do it just using kind of some algebra and some calculus. We'll get to that later, but I thought I'd show it to you now, knowing that we'll do a little bit more with it later. But for now, calculator does the job, right? Okay, so the last thing I want to talk to you guys about in this section is called the squeeze theorem. And so I think this is on that next page. There it is. Squeeze theorem, also known as the pinching theorem or the sandwich theorem. And so I thought we'd talk about this, and I'll get maybe one or two more things in here before we go. So it's descriptive. It's a very descriptive name. Something's getting pinched or sandwiched. And here is, let me get to this. Right about there is good. So notice this statement at the top says that h of x is less than or equal to f of x, which is less than or equal to g of x. What that means is that f of x is always between them, right? Vertically speaking, f of x is in the middle of h of x and g of x. H of x would be the low function, as you can see in the graph. G of x would be the high function, and f is right in the middle somewhere. You can see that represented with the graph. Does that make sense? Okay, so if that is true, if that particular statement is true, then this statement down here at the bottom must also be true. If f really is in the middle, and if the limit, I'll circle this here, if the limit of the lower function equals the limit of the higher function, they both equal some limit L, then wouldn't the middle function have to be pinched down to the same y value? So it's getting squeezed down. Like over here, f can be whatever it wants, right? In between those, at least it's kind of going all over the place. But as you get closer and closer to c, because f is between g and h, if g and h are approaching the same number, then f has to be approaching that exact same number. Does that make sense? It's kind of like in, let's say, like soccer or football. If you're chasing somebody down, you take the angle, right? Even in basketball, it's true, right? You take the angle. If I'm trying to chase somebody down, right? If somebody's running up that sideline, if we think of like the little metal thing on the floor as the sideline, if they're running down the sideline, if I do this, I'm never going to catch them, right? Never going to happen. But if I'm fast enough, and I'm here, if I take the angle and try and beat them to that spot, aren't I going to squeeze them into the sideline eventually? And I'm either going to tackle them or they're going to run out of bounds. One of the two. They're going to coincide with the sideline. Assuming I'm fast enough. I mean, if it's one of you guys, you could probably outrun the angle, right? But you get the idea. You're trying to squeeze someone into a sideline. Those two functions are squeezing that middle function down to a particular point. This, of course, holds true because f of x is always between. So it's getting sandwiched between g and h on whatever interval that happens to be. So I think we have the one example to talk about with this, so let's check that out. Number 9 says 4 minus x squared is less than or equal to f of x, and that is less than or equal to 4 plus x squared. Well, doesn't that mean essentially that f of x is between those two functions? Okay, and it doesn't even really give us an interval, it just says that that's true, so that must always be true, right? So we have absolutely no idea what f of x is. We have no clue, other than the fact that it's between those two functions, and then we're asked to do this. So this is a little bit different than what we've been doing, because in the past day or two, haven't we known what f of x is? And so we like try to plug 0 in or plug 2 in or blah, blah, blah. We don't have a clue. We have no idea what f is. So we could say, hey, we think it's f of 0. Right? You just plug in the 0, but we don't know what that is either. So we're going to have to use this squeeze theorem, the fact that f is between those other two functions, to try to help us. So let's see if you can do that. Let's see if you can use that squeeze theorem, work with those functions to come up with that limit as x goes to 0 for f of x. I'll let you guys try that on your own for just a few minutes here. And again, okay, did you see the squeeze theorem coming through here? Like I said, we have no idea what f of x is, but we do know that it's between those other two functions. Did you recognize those other two functions are just one parabola opening up, the other one opening down? So if we were to draw a really rough sketch of this, not that you had to do this, let's see here, it'd be 4 minus x squared would look about like that. 4 plus x squared, let's try that one more time. Look about like that. And then f of x, not really having any idea what it is, we'd know that it's between it, and also have to do something like that, right? So the way we could handle this analytically is we could say, well, we don't know what f of x is, and we don't really know what the limit as x goes to 0 f of x is, but I could do this. I could say the limit as x goes to 0 of 4 minus x squared, what's that equal to? 4. And I could do the limit as x goes to 0 of 4 plus x squared, what's that? And now we start to get this idea that, oh, maybe that middle function is getting squeezed in between those two, because as x goes to 0, both the higher and the lower function are going to 4, so then the middle function would have to go to 4. Make sense? So this is actually a way to prove certain things, and actually this is a way to prove that last limit that we did with the calculator. You could actually use the squeeze theorem to do that. So we could say, are you guys all familiar with the therefore triangle? You seen that before? Little dots. So that means therefore. Therefore we can say the limit as x goes to 0 of f of x equals 4. And if we wanted to give a reason for that, we could say that we use the squeeze theorem. And we'd be done. Okay, so what do you think? That's kind of it for section 1.3. Do you have any questions before we move on a little bit? Seemed to be a pretty comfortable one for you guys? Okay, good deal. All right, so I want to point out that for Monday, we've got a video. It's the 1.4 intro video. I'm actually going to skip a little ways past that and give you a chance to look at that. You'll recognize a little bit of that from the summer packet. But we're going to skip ahead. You saw this in the summer package. So here's the video part, for 1.4, talking about continuity, one-sided limits, different types of continuity. You'll definitely want to know those terms. Little check for understanding. We'll do all those when you come back. But for our last few minutes here today, we are going to focus on this intermediate value theorem. Intermediate value theorem, and see how this goes. I'll do what I need to do to kind of help you with this. But I think this is one of the topics that probably was not covered in pre-calc. Am I right on that? It was covered. Okay, good. Okay, so the intermediate value theorem has a condition attached to it. So we all know about conditions, right? A condition is basically if this, whatever it is, if this thing is true, then that's the condition leading to whatever it is we want. So, back in the day, you probably wanted, I don't know, like ice cream or something, and your parents maybe said, well, the only way you're going to get ice cream is if you finish your dinner, right? That was a condition attached to the ice cream. So the condition attached to the intermediate value theorem is continuity. And so we want to acknowledge that. We want to make sure that we consider that anytime we're dealing with a situation we think will be the intermediate value theorem. But there's the condition. If f is continuous on the closed interval and the value of the two endpoints is not the same, K is a y value between f of a and f of b. Then there's at least one number c on the interval such that f of c equals k. It's really well written, but it's not very clear, is it? It's just like if f of a and f of b, a picture I think is very useful here. So what I'm going to do is I'll erase this eventually, but I'll squeeze in a picture here to try to illustrate what I just read to you guys and try to give you a little illustration, just kind of using our classroom here too. So x-axis, y-axis, and here is our closed interval. We're just going to put a right there. We're going to put b right there. And so let's just build this up. We've got a closed interval, a to b, and f of a not equaling f of b. That's just saying that the y values at those points are not the same. They're different. Okay? K is some number between f of a and f of b. So I'm going to go ahead and fill these in. I'm going to say that f of a is right there. I'm going to say that f of b is right there. And so, here is f of a. There is f of, or the other way around. Here's f of b and f of a. And so k would be some number in between. Somewhere on that little orange interval that I just drew in there. Okay, so that's really kind of the setup. And then here is the finisher. They say, then there's at least one number, c. So c is going to fit within this interval right here. There's some number c such that f of c equals k. Let me just use the informal thing here. Yeah, informally this is saying that if the y value of a function passes from one y value to another, the function will have to hit all the y values in between. So let's think this through. I'll just put k here in the middle. So there's a y value of k. So I want you to think about this. Is there any way to connect f of a with f of b, those two red dots, without passing through that y value of k? No. There really isn't. And that's what the intermediate value theorem is saying. And so if I go from here to here, there's no way that I can avoid having that y value of k. I'm going to go a little further with this, but does that make sense so far? Okay. When I ask you, is there any way to connect those two red dots without going through a y value of k, there actually is an answer to that question. You could say, yes, what's the only scenario where I can avoid k? If there's some kind of a discontinuity, right? So if there was, say, a hole right about there, I just avoided k, didn't I? Totally avoided it. But remember the intermediate value theorem? The condition for that? Continuity. And so because there's a discontinuity there, we can't use that to disprove the IVT because we're acknowledging the condition is continuity. So that doesn't work. Maybe you could think of avoiding k by doing this.
What about unbounded behavior?
That's another discontinuity, right? Unbounded behavior. Let's see here. Let's go with that. So unbounded behavior, check this out. You could have a vertical asymptote. You totally avoided k, didn't you? But again, it's a discontinuity. And so the condition for the IVT is that we have a continuous function. It's a little bit of a dry example. I can give you a less dry example. I was talking about this the other day with folks that were here for the little summer session with Colin, yeah. So just think about this in maybe a little more practical manner. If I am standing in this room, and we all know that this room is pretty well locked down other than the door, right? There's no other way in or out, right? It's just the doorway right there. That's the only way to get in or out, as far as we know, other than if we try to run through the wall. We're just not going to count that. Or jump out a window. Not going to count that either, right? So if I'm standing right here, and you're all paying attention and everything, and then you kind of get distracted or, kind of lose focus a little bit, and the next thing you know, I'm standing out in the hall. You never really saw me standing in the doorway, but couldn't you assume that I actually at some point was in the doorway? Right? So like my y values are in here, I'm walking around, it's my position in here, and then I'm out here talking to Braden. And even if you didn't see me stand in the doorway, don't you know for sure that I was actually in the doorway? Isn't that an IVT concept? If I'm in here, and then later on I'm out there, didn't I have to at one point be in the doorway? What would be the one exception to that?
Jesus Christ.
Yeah. Or some magician that could fool you, right? If I could somehow teleport myself from here, and then I'm gone, and the next minute I'm out there, right? So in that case, then my position could be described as not continuous, right? Because I was here, and I didn't exist for just a brief moment, and then I was out there, right? So my motion path would be discontinuous, so the IVT wouldn't even apply anyway. So are you getting a sense of the IVT? If I'm here, and then I'm there, I had to hit all the y values in between. That's it. I've got to, it's got to be a continuous path, but that's kind of the essence of it. So let's take a look here really quick. This will be just about right, timing-wise, at this one example, and then I think we've got another example we'll do next time. And watch the video. The video gets into details that some of you saw, and really we talked a lot about over the summer in regard to continuity, some of the real detailed stuff, and you want to know that. But we'll talk about that on Monday. But for now, let's take a look at example A. It says, use the graph of f of x, and the IVT. I don't know about the whole, I'm going to get rid of this. I don't know why that's in there. I don't know if we really need to use the graph. Let's just use the IVT to prove that that function has an x-intercept on 0, 3. Just going to use the IVT. You're welcome to use that abbreviation. I know what that is. You know what that is. The AP readers would know what that is too. So feel free to use that abbreviation if you care to. But we're going to prove that that function has an x-intercept on the interval from 0 to 3. Prove that that function has an x-intercept on the interval from 0 to 3. And this is a really important point. We're about to use the IVT. So since we need to at least mention that the condition for it has been met. And what's the only condition for the IVT? Continuity. So we want to say that f of x is continuous, and then we'll try to work within that IVT to prove what we want. Okay, so tell me about x-intercepts. Tell me whatever it is you know about x-intercepts, because we're trying to work with it. So what might be some useful information? Y is equal to 0 at an x-intercept, right? Okay, so we're starting to talk a little bit about the IVT, because remember the IVT says if I know that I got a y value here, and a y value here, then I got to hit all the y values in between. So if an x-intercept means that we have a y value of 0, we're not really looking for what the x-intercept is. We're just looking to prove that it exists. Right? So if I'm trying to prove that y is 0, what might be some foundational stuff that I'd need to then go on to say that, yeah, y has to be 0 somewhere in there? If I could show that I've got a negative y value somewhere and a positive y value somewhere, you following me? Then to go from a negative to a positive, what do I have to go through? If f is continuous, I have to go through 0. And we look at this. This is a parabola, right? It's a polynomial. And all polynomials are continuous. And so our little statement there that f of x is continuous is definitely true. So all we got to do now, before we tie this up, is to prove somewhere that there's a y value that's negative, and somewhere else there's a y value that's positive. How might we do that? What do you think, Jack?
Pick 0 and 3 in.
Okay, so why did you pick 0 and 3? Because there's a lot of other numbers in there.
Because they're going to be on the end.
The endpoints.
Yeah, the endpoints, and so that will give us the bigger.
I think that gives you a fair chance. I don't think it's a guaranteed thing, but I think it gives you a fair chance. So let's try that. Do you see he's saying let's plug in the 0, see what happens. Then let's plug in the 3, see what happens. We good with that? Okay, so let's try it. So f of 0 is what? F of 0 is 8. Okay, so we have half of the puzzle right here because 8 is positive, right? 8 is above 0. It's higher than 0. And then he also suggested to plug in a 3. And when you plug in a 3, what do you get? Negative 1. Okay, so Jack has chosen some wise numbers, right? Because we have the pattern now. We have a y value that is above 0 and a y value that's below 0. Can I play devil's advocate just a little bit? Because he picked the right numbers. Maybe he thought them through a little bit. It was smart for sure. What if you didn't pick 3? What if you chose, instead of a 3, so let's just pretend like that's not there. What if you chose, say, a 2? Because wouldn't 2 be reasonable? Isn't 2 in the interval? So if you plug in a 2, what do you get? You do get 0. So that, now this is, you know what? I wasn't planning on this. That brings up a very interesting point. So if you plug in a 2, you do get 0. And so you might be tempted to say, hey, there's the 0. But I want you to look really carefully at the instructions. The instructions said use the IVT, This might be a frustration point for you, but if you were to do that and say, hey, I know there's a 0 because I just found it. True, but did you use the IVT? Did you follow the directions? No, you did not. So I'll be, in a question like this, I would be looking for evidence that you used the IVT. Just finding the 0, like, couldn't you have just factored it and found the 0? Or used the quadratic formula or something? You didn't use the IVT. So I'm going to be looking for elements of that. So that's a bad number, Mr. Anderson. Let's try a different number. What if we tried 1? If you plug in a 1, you get 3, don't you? That's also positive. So if you were using this one and this one, you'd actually be in a bad place because you've got a positive y value and a positive y value. Does that mean that y had to go through 0? No. A positive to a positive, it did not have to go through 0. But if you did use the numbers that Jack so wisely chose, then you've got what you need because you've got a positive y value, a negative y value. You can then go, therefore, f of x had to equal 0 at least once. It's supposed to be an L. On the interval 0 to 3, therefore f of x has an x-intercept on that interval, at least once, right? We know for a fact that it is just one time only on that interval, but we can only prove its existence at least one time, not necessarily more. Okay, question?
Problem. When if it was like 0 to 2,
Yep.
and then it'd be 2 would equal 0, f of 2 would be 0.
That means I wrote a bad question. Yep. Yeah, if you can't, and something to think about here, like I would say this would definitely be, say on a quiz or something, a no calculator question. I would expect that you'd be plugging in just integer values. You know, I'm not going to put you in a place where it's like, oh, gee, if you'd only have picked 1.67, you would have been okay. I'm not going to do that to you without a calculator. And so if the scenario happened, you just said, I just wrote a bad question. And that's very possible, but I try very hard not to. Yeah, fair question. Well, and your conclusion there would be, I don't know. The IVT doesn't prove anything, right? You wouldn't be able to prove what you were supposed to prove.
Okay.
Okay, that's it. Question, Johnny?
What if you were trying